while you guys are doing copying this down, I will talk about today's lesson fact, which is one of the longer lesson facts. 48 and 75 are betrothed numbers. What are the factors in 48 and what do they add to? So betrothed, so 48, the factors of 48 include 1, 2, 4. Well, what is a betrothed number? Caitlin, you're about to find out what a betrothed number is. 1, 2, 4, 8, because 6 8s are 48. So then, oh, whoops, that means 6 is also a factor. Whoopsies. 6, 8, 12, because 12 times 4 makes 48. 2 times 24 is 48. And then you would also need to take in 48 itself. But if you take all of these numbers here, right, you go 1 plus 2 plus 4. 1 plus 2 makes 3, plus 4 makes 7, plus 6 makes 13, plus 8 makes 21, plus 12 makes 33, plus 24 makes 33, plus 24 makes hold on, I made a mistake. No, I didn't make a mistake. I got myself confused, I think. So if you add all of those together, let me double check this because I think I may have made a mistake. 1 plus 2 plus 4 plus, this is not part of the lesson, by the way, guys. This is just me stuffing around a little bit at the start. Plus 24 makes 57. Plus 48. Huh. No, I made a mistake here. I must have missed a factor. 48. It's not divisible by, it must be divisible by 3 as well. Yep. 3 and 16. Good job. So 1 plus 2 plus 3 plus 4 plus 6 plus 8 plus 12 plus 24 equals, that's 16 plus 16 equals 76. No, I got this wrong. I have to figure this out later on. So the point is what is a betrothed number? Betrothed numbers means it means a promise to another person, like a fiance. If you promise to marry someone, then you're betrothed to that person. And if you actually take all of the factors of 48, they will equal 75. And if you actually take all the factors of 75, they actually equal 48, except don't add 1. So I added 1, that's why I got to 76. So that's interesting. Amicable numbers are the same. Amicable numbers are the same, but they only work if you include 1. So 220 and 284 are amicable numbers. So if you take all the factors of 220 and you add them together, it equals 284. You take all the factors of 284 and you add them together, it will add to 220. So they're like the lovers. So it's like if you ever wondered, oh, do numbers ever have a pair? Do numbers ever have another number that they fall in love with? In this case, you would say that 48 loves 75, and 75 loves 48. What are the factors of 75? 1. There would have to be 75, which we're going to ignore. We haven't got 2. We've got 3. 3 times 25 is going to make 75. So then that means we've got 5. What's 5 times 84? That's going to be 8 5s are 75. 8 5s are 8. 8 5s are 40. 16 5s. 5 times 15. I'm going to go with that. And so if you add those together, because it's the 5, 6, 7, 6. 6 times, sorry. Yeah. So if we add these together, then that equals 45 in theory. 1 plus 3, 3 plus 5 makes 8 plus is 30, 48. Yeah, 48. Yay. Makes 8. That makes 40. Add them together, 48. So it does work. But that's not the point of today's lesson. All right, if you guys are falling asleep, let's come back to reality. Lesson 48, linear programming. We'll be able to use the corner point principle to evaluate an objective function. So today, I have to teach you two main ideas here. Firstly, what is the corner point principle? And secondly, what is the objective function? So both of those two are two different ideas that we need to cover in today's lesson. Before we do that, let's grab a look at what we did last lesson. Last lesson, we talked about what corner points were. We said that a corner point is a point in a feasible region where two boundary lines meet. So if you've got a boundary line, you've got two boundary lines like this or two boundary lines like this, it's the point where they meet. The corner is not included in the feasible region if one of or both of the lines are not included. So therefore, even though this is still a corner point, it's not included in the region. Corner points must be labeled on the graph. So you can't just put a corner point in. Then what we did is, as a group, we worked on this one here where we learned how to graph. We graphed this here, which was, I think, came out to be like this. And then we had this, 4 plus a half. And then we said this was the feasible region. So then the goal was to find out what the corner points were. So we found out that this one was 0, 0, and we got all 4 corner points. And that was all we need. We ended up doing at the end of the lesson. Then I told you guys to start working on 12E, and I gave you guys a fair amount of time to work on 12E. So when we come back, and pretty much when we expect that you guys have finished 12E. Now after 12E, we're going to work on this idea, linear programming, and specifically these two things. So to start off with, let's talk about what we mean by objective here. An objective function is a quantity you want to make as large or small as possible. Okay? Now, the reason I've got a picture of a map here is sometimes you might have a military objective, or you might have a company objective. Our objective is to get as many people buying Mitsubishi cars as possible. That's the objective. Or your objective might be, we want to get from this point onto this point on the map as quickly as possible, or with as few steps as possible. So there are different types of objectives. In this case, we always want to look, when we have an objective, we'll either be trying to minimize it or trying to maximize it. Those limits on this, the limits on this function are your constraints. So you might be like, hey, cool, we could make like millions of dollars if we just sell, we could make millions of dollars if, well, not maybe millions, we could make hundreds of dollars if we sold everything in the store, including the cash register and rugs and the door handles and stuff. But you have some constraints, which might be, you're not allowed to sell, and you're not allowed to sell any of the equipment. You might be like, oh, we'd make a lot more money if we stopped paying our staff. So there might be another constraint, it's like, actually, you've got to pay your staff. So it's like, how can you maximize the amount of money without by following these rules? So some examples of some objectives could be minimizing costs, or maybe minimizing travel time. So if I said, right, I want you to drive from Melbourne to Ballarat, and I want you to minimize the time, well, that would be an objective function. And in fact, that's what AI tries to do. It tries to minimize the travel time, because that's its objective. They could be maximizing profit, or maybe classroom marks. Maybe you want to make sure that you get as much money as possible. So how can you, get people to work, maybe sell things at a certain price in order to make sure that you get the most amount of money. So that's the idea of what an objective is. What we're going to do now is we're going to talk about, well, how can I then add numbers to an objective function? It's one thing to say, oh, cool, our objective is to maximize my marks in general maths, but how can I do that? Like, how can I measure that I've succeeded? So what I'm going to show you now is this. I'm going to change the slide. If you guys need me to stick around the slide a little bit longer, then let me know in the chat, but otherwise I'm going to keep going. Okay, so objective functions. You own a burger restaurant. Your objective, there's no pencil here. I just thought I would throw this up here. Your objective or goal is to make as much money as possible. So you want to keep your costs down, okay? So if you want to keep your costs down because you want to make sure that you want to come home as rich as you possibly can. So let's just say that you've got a manager, and a manager costs $18 an hour. And you've got a team member, and a team member costs $14 an hour. Then that means that you have your costs here. Your costs are equal to 18 times the amount of managers plus 14 times the amount of staff team members. So looking at that function, there are values of M that would, if you want to minimize M and T, there are values of M and T that will make a really, really low cost, right? So if you're going to have a low cost, the lowest possible cost would be to have M equals 0 and T equals 0. Pardon me. Because if you make M equals 0, T equals 0, the cost of your staff is equal to 0. But would that be a very good burger restaurant would that be a very good burger restaurant if you had no like staff? What do you guys think? Would that work? A burger restaurant without any staff?
No.
Thank you for quickly giving me the answer there. No, that wouldn't work. Let's use our obvious logic here. So then you might say, okay, fine. Well, what if I only have, what's another way that I could minimize costs? What if I had like no managers, but two team members? Well, now your C is going to equal 18 times 0 plus 14 times 2. So your C is going to equal 28. So that's not as low as 0, but at least now we've got people working there. But you might turn around and say, oh, but if we just had 2 team members and no managers, then like it's cheaper, but maybe those team members won't do any work, or maybe they won't know what they're doing. So maybe you decide that you want to have 1 manager and 1 team member. And sure, that's going to be that's going to give you a cost, which is going to be 32, which is more than 28, but now you've got, a restaurant that can actually work. And so you might say, actually, you need to have one manager for every 2 team members or something like that, because otherwise it won't work. You might say, actually, you know what? We have to have at least 1 manager. You can't have no managers. You could say you can't have no team members. And the last thing would be this. You couldn't have maybe 2 managers, right? And no team members. But that's going to cost you, in this case, $36. So it's really expensive. In fact, this is probably one of the better ways to go. You still have a manager, you still have a team member, but it's as cheap as you can. So what we're going to do is we're going to explore, okay, well, how would that work in a mathematical setting? How would that work in an actual example? So what we're going to do is and later on, So we're going to come back to this idea later on. So this idea that we're talking about with like actual real world examples, we're going to come back to. But at the moment, we need to get our grips on, okay, how can we do this with numbers first? And then what we'll do is we'll introduce like worded examples and stuff like that. So first up, let's look at the corner point principle. The corner, you don't need this picture, by the way. The corner point principle means the maximum and minimum values of an objective function are found at the corners of the feasible region, and that they're only found at included corners. So if your feasible region is here, then the corner points, one of these corner points will be a maximum. And one of these corner points will be a minimum. Like one of these corner points will be a maximum. It'll be the highest point in that region for a particular objective function. And one of these corner points will be a minimum, maybe even two. And this is another example of using, in this case, we're using 1, 2, 3, 4, 5 lines, 6 lines, 1, 2, 3, 4, 6 lines to get 1, 2, 3, 4, 5 different coordinates. 5 different. And by the way, at the top right-hand corner are the equations that are used to generate this function, this picture. I think this is based off, yeah, so this is based off the burger question. So we've got M and we've got T. So this is like this is like what you would do is you'd be like, okay, cool. So you might say, you have to have more than 2 staff in the restaurant. And this says you have to have at least 1 manager. That makes sense, right? You can't have like you can't have a store without any managers, because then who's going to lock the doors and who's going to, like, you know, count the cash at the end of the day? You've got this function here which doesn't make much sense to you. M must be greater than T on 4. What that means is for every 4 staff members you have to have at least 1 manager. You have to get, so if I have 8 staff, 8 divided by 4 means I need 2 managers. If I have 12 staff, 12 team members, 12 divided by 4 means I need 3 managers, and so on. And the last one is M plus T must be less than 10, which means that the total number of managers has to be less than 10. You can't have total number of staff must be less than 10. You can't have too many people in the restaurant. Maybe if you had 20 people in the restaurant, then it would just be too much. And so what you can do is you can use these corner points to see, well, which of these is going to be the cheapest and which of these is going to be the most expensive. No, you don't have to copy down the graph. I'm just showing the graph as just a little way. So if you remember the formula, if you got, the formula was 18M plus 14T, right? Look here, this point here is going to cost $180 to have 10 managers working, which is crazy. Down here, this is going to cost you 8 times 18 plus 14T. We're going to do this in actual real time in a second. I'm just showing you here. We'll just do one more example. 18 times 2 plus 14 times 8. This is going to cost you $148. So it's a lot cheaper to get this compared to this. And I actually think that this point here will be the minimum. But you don't need to know that. You just need to know that the corner points is where the objective function gets solved. What we're going to do now is we're going to do a big example. And then that's going to be it pretty much. Yeah, okay, that's for, yeah, that's going to be quite challenging. Yeah, okay, that's for 12H. So cool. We're not going to do that yet. We're just going to go back to here. Sorry. So we're going to graph the feasible region, but then what we're going to do is we're going to look for, we're going to label the feasible region, and then we're going to maximize the objective function. So the objective function is P equals 2x plus 3y. So what I'm going to do is I'm going to give you guys a second to get a 10 by 10 graph into your book. We're going to maximize this. I'm going to look for a ruler that I can use to draw this graph, and then we'll get started. Ruler. I swear I have a ruler somewhere. There we go. Okay. I'll give you guys a little bit longer just to get ready. We're going to have to copy down these formula too, by the way. So this is going to take us a little while to work through. So be patient. All right. And hopefully my goal, by the way, ladies, is to try and get this done in about 15 minutes so that you guys have got some time to start working on the next topic, which is 12G. So here we go. First one, x is greater than 0, y is greater than 0. These two are easy. By now, you guys probably are a little bit familiar with this line here. This green line here represents x is greater than or equal to 0, which means that all of this region here is ignored. And this line here, which I'm going to draw it there, means that all of these values, this is y is greater than 0, because all those values we can ignore. Now we're going to start to get into some interesting territory. In dark green, not that it matters, we're going to do this one here. How do we do that one? Well, first what we would do is we would write down the formula with an equal sign. I would then plot that. I'd say let x equals 0, let y equals 0. That gives you when x is 0, y equals 7, and y is 0, x equals 7. So it gives you 2 points, 0, 7, and 7, 0. Oop, yeah. So putting those in, bang, bang, gives me this line here. Beautiful. And then I'm going to check a value just to make sure that it works. You might wonder, why am I asking, hey, let's pick a student. You're Caitlin. Why do you think that's? Because I'm just like, I just want to get through this relatively quickly. And in fact, I think the more interesting part is going to be the subjective part. So what we're going to do is we're going to check 0, 0. So that means 0 plus 0. Is that less than or equal to 7? Yes, it is. So therefore, 0, 0 is in the region. So that means everything that is more than this, is not 0, 0, will be crossed out. Perfect. Oh, and this line is x plus y. Oops, let me do this in a different color so we can see it. X plus y is less than or equal to 7. Beautiful. Now we have one more line that we need to draw. Let's do that in blue. 2x plus 5y must be less than or equal to 20. So I'm going to do that here. It's a bit challenging for me, ladies and gents, because I haven't got as much space as I would normally have on a whiteboard. 2x plus 5y must be less than or equal to 20. Let's do the same thing. Let x equal 0. Let y equal 0. That's going to give you 5y is less than or equal to 20, which means that y is less than or equal to 4. Sorry, that should be, whoopsies. Sorry, guys, that should be equals. Y equals 4. Let's put that on there. When y equals 0, we get 2x equals 20, which means x equals 10. So it's going to put that down there, 10, which gives us this line here. And you're like, cool, great, all right. Now what we need to do is we need to check 0, 0. We can check any point, but I like to check 0, 0. Check 0, 0. So therefore is 2 times 0 plus 5 times 0. Is that less than 20? Is 0 less than 20? Yes, it is. So therefore this is in the region, everything else is not. So we're going to cross it out like so. Oops. Whoops. Ah. That'll do. Oh, I need the actual equation. Two x plus 5y is less than or equal to 20. So there we go. So we can now see that our feasible region, I'm actually going to highlight it in red just so that we can actually see it clearly, is here. And sometimes this is actually a good idea to do during a test, is just to like re-go over your feasible region so you can easily see it. If you've got a red marker, great. If you haven't got a red marker, then just, you know, crap. Sorry. I keep accidentally pushing the buttons on the actual pen, which is very actually difficult to not do. Okay, let's try this again. Sorry, guys. I'm just gonna freehand it because like using a ruler is actually preferred. So then I'm just gonna write feasible region. Actually, I'm not gonna do that there. I'm gonna do that over here. The feasible region is this box here. Now we're not done. We are not done because we have to now label the feasible region, and now we need to label the corner points. So what are the corner points? Well, we've got 0, 0. We've got 0, 4. We've got 7, 0. And then whatever this point is. So that point happens to be where these two lines intersect. So how do we find that? Well, you know, we've got, how do we find that? Well, let me just rub out this now. I'm going to need the space now. How do we find this intersection point? Well, we've got these two equations. X plus y equals 7. And then I've got 2x plus 5y must be equal to 20. Now, there are a couple of ways you could do this. Fastest way. Multiply everything in here by -2. It's going to give you -2x, -2y, -14. Why? Because then when I add these two things together, that gives me 3y equals 6. Y equals 2, which means that x plus 2 equals 7, x equals 5. So this point here is at 5, 2. If you didn't know how I did that, what I did here is I actually did a really quick version of the elimination method. I multiplied both of these by -2. And then I added these two equations together. So that canceled out the x's. That's why I got 3y equals 6. Once I got this, I substituted sub y equals 2 into 1. And then that's how I got x equals 5. So there's your feasible region with the labeled feasible region with corner points. Now there's only one little bit here. We've got to maximize our objective function. Now this is something that's new. We haven't done this before. I'm going to do this in black. And I'm going to do this at the top. Now, how you would do this part is you do something similar to this. We have 4 corners. Those corners are 0, 0, 0, 4, 7, 0. Hold on. I need more space. We've got 4 corner points. 0, 0, 0, 4, 7, 0, and now 5, 2. What we're going to do for each of these is we're going to test our objective function. So in this case, P equals 2x plus 3y. So we would check this. And that would be P equals 2 times x, which is 0, plus 3 times y, which is 0, gives us 0. Okay, what if I look at this point here? Well, that would be P equals 2 times 0 plus 3 times what's y? Y is 4. 3 times 4, which is equal to 12. Okay, let's look at the next one. P equals, in this case, we're looking at this one down here. We've got 2 times 7 plus 3 times 0. Because y is 0. That's going to give you 14. Hey, we have a new. And the last one, we've got P equals 2 times 5 plus 3 times 2. That's going to give you 16. So out of these corner points, according to the corner point principle, one of these will be a maximum. And it turns out the maximum is this point here, because it's the largest of all of them. So maximizing your objective function, the maximum is at 5, 2. And that's where our function is maximized. Our function is maximized at 5, 2. So what time have we got? Yeah, that took us about 15 minutes. Let's break this down into step by step what we did. And yeah, this is a big question, all right? This is like almost as big as they get. There's not quite. And with questions like this, when they show up on tests and exams, it's not like, all right, go. We usually step you through the process. So the first thing we did is we learned how we graphed all of the lines on. We graphed all of the lines on the graph, and then we turned them into inequalities by checking 0, 0. Once we did that, what we did is we then found out where the corner points are. You should show all the intercepts, yeah. Once we've found all of the intercepts, that's what we can do is we can then say, well, now we know all the intercepts, we've labeled the feasible region, we can now check the objective function. We check the objective function by checking it against every single corner point. Sometimes this might take a while, especially if you've got 4 or 5 corner points. So this might take you a little bit longer to do than usual. And then once you've done that, you then ask, am I looking for a maximum or a minimum? In this case, it asks for the maximum. So we're looking at 5, 2. If it said the minimum, then it would be 0, 0. And that's how you go about graphing these types. That's how you go about using the objective function. Now, what we're going to do now is, actually, before I do that, before I move on, are there any questions? Are there any questions or queries about anything that I've done here before I move on, I should say? Any part of this confusing or like doesn't make sense? Oh, good, we've got a question. Okay, this slide, or so someone said they haven't finished copying down the other slide. Do you mean this slide here? The one that's all, yeah, okay. So I'll keep this up for a little bit longer for those of you guys who want to copy this down. Whilst that last person is copying this down, are there any other questions?
Wait, so can you explain the objective function again?
So the objective function is about trying to maximize or minimize a number. So what we know is that we want to find out how can we make P as large as possible, okay? Why do we want to make it as large as possible? Because it asks us to maximize this function. But we can't just, obviously the maximum value for P would be X equals infinity and Y equals infinity, or X equals 99 million and Y equals 99 million. But the problem is that we said, but there are limits. You can't have X be bigger than 7, essentially. If X is bigger than 7, it doesn't work. You can't have X be negative. So we've got to make sure that we follow these rules. So that means that it must be somewhere in this feasible region. That is somewhere in that feasible region, you will get your maximum. And then I said, the maximum is going to occur at one of these corner points. Why does the maximum occur at one of these corner points? Because it's at the edge of what's allowed. So what we need to do is we need to check all of the corners that are included. It just so happens that each of these lines is included because they all have a equal to. So we have to check each of these 4 corners. So once I've checked each of these 4 corners and I run the coordinates through the objective function, I get these values for P. And that means the highest value that I can get for P is 16. That's as big as I can make P. So that's how we use the objective function. The objective function says make P as big as possible. To make P as big as possible, I can make X equals 5 and Y equals 2. There is no other point in that. There are no other points in this feasible region that would make P any larger than 16. And I know that because according to the corner point principle, the maximum occurs at one of these 4 points. Does that help? Does that answer your question? I don't know. I
Yeah,
can't
sir,
hear-
it does.
Okay, cool. Are there any other questions? Are there any other queries? All right, I'm going to get rid of this slide now because what I want to do now is I'm going to close this.